Good afternoon. Today, I'd like to talk about the importance of microscopic nuclear cross-section data and why improving it matters for future space exploration. As humans prepare for longer missions to the moon and eventually to Mars, radiation becomes one of the biggest engineering challenges. Engineers really rely heavily on computer simulations to predict how radiation interacts with spacecraft shielding and how much radiation astronauts will receive. These simulations depend on microscopic nuclear cross-section data, which describe the probability that particles such as neutrons will interact with different materials. Mhm. Before looking at current applications, it's important to understand the challenge. Unlike many engineering properties, microscopic cross sections are not constant. They change depending on the neutron's energy, the isotope being struck, and type of nuclear reaction taking place. One particular difficult region is called the resonance region, where very small changes in neutron energy can cause very large changes in the probability of interaction. Because of this behavior, it is practically impossible to, it is very difficult to experimentally measure every isotope at every possible neutron energy. Instead, engineers on rely on evaluated Instead, engineers rely on evaluated nuclear data libraries such as ENDF, JEFF, and JENDL. These libraries combine experimental measurements with theoretical models to estimate cross sections across a wide range of energies. As a result, radiation transport simulations are only as accurate as the nuclear data they use. Today, these nuclear data libraries are used extensively on radiation transport simulations. Organizations such as NASA use transport codes like Altar, OLTARIS, while researchers commonly use Monte Carlo codes such as MCNP and GIN-T4 to simulate how radiation travels through spacecraft materials. These simulations begin by defining the space radiation environments such as galactic cosmic rays or solar particle events. The transport code then uses microscopic cross-section data to determine the probability that particles will scatter, be absorbed, or generate secondary particles as they travel through shielding materials. Using these simulations, engineers can estimate astronaut radiation dose, compare different shielding materials such as aluminum or polyethylene, and optimize shield thickness while minimizing spacecraft mass. Without accurate cross-section data, these predictions become much less reliable. Although today's transport codes are extremely powerful, they are not perfect. Uh, there have been several studies that have shown that different transport codes can produce noticeably different radiation dose predictions for the same spacecraft configuration. Much of this uncertainty comes from differences in the underlying nuclear interaction data and the physical models used by each code. Improving microscopic cross-section measurements would reduce these uncertainties throughout the entire simulation process. More accurate nuclear data would improve radiation dose predictions, help engineers select better shielding materials, increase confidence in spacecraft design, and ultimately improve astronaut safety during long-duration missions beyond Earth orbit. As future missions become longer and more ambitious, reducing uncertainty in radiation transport simulations will become increasingly important. To conclude, microscopic nuclear cross-section data from the foundation of modern radiation transport simulations. Today, engineers use these data to design spacecraft shielding and estimate astronaut radiation exposure using tools such as OLTARIS, a simulation that NASA uses, simulations such as tools such as MCNP and Gene T4, spelled GEAN T4. However, uncertainties in nuclear data still propagate through these simulations. By improving microscopic cross-section data, we can reduce uncertainty, improve shielding optimization, and make better engineering decisions for future deep space missions. As human exploration extends farther into space, improving nuclear data will continue to play an important role in protecting astronauts and enabling safer exploration. Thank you for your time. I'd be happy if you have any questions. And that concludes my speech.